Hello everyone. I hope everyone is well. So last time we went through section 4.2 and 4.3, and I also asked you to try some homework questions. So this time I'm hoping to go over the homework questions. I'm not going to go over them all. I'm going to go over a selection, so it'll be just as though we were in class and people had raised their hand and asked questions. I'm going to choose to go over even ones where it makes sense, because the odd numbered ones, of course, at least have some kind of answer in the back. So I'm trying to give people a chance to try the ones around the ones that I'm doing. So what you're looking at on the screen here, of course, you're looking at the browser so that I can do stat key, and I'll need to do stat key from time to time. And here, this is just simply a piece of paper, and I'm just simply gonna write on it. That's all. And just going to try to do the homework again as though it were at the board. Okay, so what you want to have then in front of you is you want to have the book, either the paper book or the online book, and I'm on section 4.2, page 281. And again, I'm just simply going to go through the homeworks and see how it goes. So I'll start with Skill Builder 2 on page 281, and I'll read it. It says, the null and alternative hypothesis for a test is given, as well as some information about the actual samples and the statistics that's computed for the randomization sample. And then what we have to do is indicate where the randomization distribution will be centered. In addition, indicate whether it's left tail, right tail, or two tail. Okay. And I'm going to do number 46, just again because it's an even numbered question, that's all. So if you have the book open, if you're able to read the material, the hypothesis is H naught is that mu equals 10, and HA is that mu is greater than 10. The sample x bar equals 12, the standard deviation of the sample is 3.8, the number in the sample is 40, and the randomization statistic is x bar. Now there's a lot of things there, a lot of numbers, and they're designed to be a sort of a cloud of things that could confuse you. So you want to think again about what the hypothesis test is. In a hypothesis test, the alternative hypothesis people are discussing things, arguing things, with the null hypothesis people. The null hypothesis people are asserting that the true number, the population number, the census number, in this case mu, is really 10, and if you observe something other than 10, it's only because of routine sample-to-sample variation. Your x bar in your sample number, will differ from 10 only because of routine sample-to-sample variation. HA, the alternative hypothesis people, are the people who think that there's something for real here. They're asserting that mu is greater than 10. They're not saying that mu is equal to 12. They're saying, though, that mu is greater than 10, and the fact that our sample came out to be 12 is evidence of that. In an argument between these two groups, the HA people, in order to convince the H naught people to change their mind, in order to reject H naught, the HA people have to be able to say, suppose you're right, H naught people. Then the distribution of samples would look like so-and-so. That's what this question is about. The distribution of samples would look like so-and-so, and our sample is way, way out there. So it's hard to believe that you could be right. So that's how a basic hypothesis test works. And I've many times talked about the example of somebody walks into the room and starts flipping a coin. And the nominal thing we think is, well, it's a 50-50 coin. So we are, in that context, we are the null hypothesis saying P equals 0.50. But somebody says to me, no, look, this guy's an amazing coin flipper. He can get heads far more often than he should. That's an alternative hypothesis person who is asserting that P is greater than 0.5. If that person flips a coin 100 times and gets 53 heads, I'm like not convinced. If that person flips a coin 100 times and gets 83 heads, I'm like, whoa, I guess I'm changing my mind. I guess that for this person, P is not 0.5. Okay, so the key point here for this question is that the alternative person says to the null person, suppose you're right. And then they get a distribution of samples. That means, because of the suppose you're right, that the samples should be centered around the null hypothesis people's true number. The null hypothesis people think that mu is actually 10 in this problem. So the sample should be centered around 10. So when it says in the question, indicate where the randomization distribution will be centered, the answer is 10. not the 12, 10. And then the other thing, it says left tail, right tail, or two-tailed. So if you're reading the book, it says mu greater than 10. So we're interested in samples, X bars, that are bigger than 10. So that's a right tail, because numbers are on the number line are bigger when they're to the right. Okay, so again, the answer is 10 and right-tailed. Okay, on to Skill Builder 3. It says a randomization distribution is given for the hypothesis test and shows what values of the sample statistic are likely to occur if the null hypothesis is true. Several possible values are given for a sample statistic. In each case, indicate whether seeing a sample statistic as extreme as the value given is number 1, reasonably likely, number 2, unusual but might happen occasionally, number 3, extremely unlikely. Okay, and then they point me to figure 4.13, which is down at the bottom of the page. 4.13a shows a randomization distribution for a hypothesis test with p equals 0.30. And because the null hypothesis says p equals 0.30, I'm seeing that this randomization distribution does seem to be centered around 0.30. And then they ask me now, suppose somebody's sample number, somebody's p hat, suppose somebody's sample number is p equals 0.10. I look on that graph and I ask myself, is p hat, is p hat equals 0.10 a way off, crazy, unbelievably, hardly ever happen sample? Is p hat equals 0.10 rare but possible? Or is p hat equals 0.10 every day? And looking at the distribution, and again, you should look at this in the online system that you have. Looking at 0.10, it seems to me that 0.10 is pretty rare. I'm just eyeballing it, but I think 0.10 is in the only 2 dots down their range. So I would personally call 0.10 extremely unlikely to occur. And then it says p hat equals 0.35. Looking at the randomization distribution, I ask myself, do samples like 0.35 happen every day? And the answer is yes. They do happen every day, looking at that picture. And then the last one is p hat equals 0.60. And again, looking at the picture there, the 0.60, I don't think that one's a borderline. The first one might have been borderline. A person could say, well, it's kind of rare or it's very rare. But 0.60 is very, very rare. Hardly ever happen. You know, sort of darn near impossible case. Okay. Scale Builder 4, it says a randomization distribution is given along with the relevant null and alternative hypothesis, which p-value most closely matches the observed statistic. And again, I'm doing an even number, so the first one happens to be an even number. It says figure 4.14 shows a randomization distribution for testing h0 of mu equals 50. And again, a person notices it says mu. That's the population parameter, that's a census number, that's the true number, that's the value that we're talking about that we don't know. So mu equals 50 versus HA of mu greater than 50, and in each case use the distribution to decide which value is closer to the p-value for the observed sample mean. So you look at the graph there and it says suppose somebody reports a sample of 68, and you ask yourself, does it seem to me that if I took all the dots 68 and above and colored them, that would have a 1% of the total dots, or would that be 25% of the total dots? So again, you look on the graph, take all the things 68 and above. Do you think that's 1% or do you think that's 25%? And in my eye, for question A, there's no way that it's 25%, so it must be 1%. B, p-value for x bar equals 54. So I'm supposed to look at x bar equals 54 and shade all the ones that are greater than 54, greater than or equal to 54, and ask myself, is that, it asks me 10% or 30% of the total. So looking at the graph, shade all the values 54 and above. Is that 10% of the total or is that 30%? And there's no way that it's 10%. So I'm calling that 30% of the total. And last, part C. The p-value for x bar equals 63. 63 is closest to, is it 5% or 50%? So for 63, again, there's no way that it's 50%. So I think 63, you're only looking at something like 5% of the total values are 63 and above. So I'm calling that the 5%. So that's the p-value. I'm trying to guess what percentage of the area is colored if you shade that number and above. Okay, just a couple more here. Let's see, Skill Builder 6. It says, gives a null and alternative hypothesis for the population proportion. as well as sample results, use stat key. Of course, that's why I have stat key here. Use stat key to generate a randomization distribution and calculate a p-value. And it says use test for single proportion, and then edit data to enter the sample information. And I'm going to do number 40 and number 60 and number 62, because again, those are the two even numbered ones. So 60 says hypothesis test is H naught is p equals 0.5 and HA is p equals less than 0.5. Excuse me, p less than 0.5. And then they give a sample data. So I'm going to get rid of the paper here on the screen, and I'm looking at stat key, and I need to do its test for a single proportion. There we go. And I need to edit the data to be what they want it to be. They want it to be 30 out of 50. So 30 out of 50, 50, 50. Okay. And I have it right. The required p is 0.5. That's what it says in the question. So I think I have it all entered right. N equals 100. So right. So they want me to generate 100 samples. So they say test for single proportion, edit data, enter the sample information, and then there we go. And now they want me to know here to generate a random distribution and generate estimate the p-value. So 38 out of 100 is 0.38, and it's a left tail because it says p less than. And now I'm not interested in 0.36. I'm interested in 0.38. So 0.38, 0.38, and okay. And it says that that's a total of 5% of all the dots. So the p-value is 5%. Oh boy, it doesn't come out very well on this screen, does it? So those are red on my screen. I apologize, they don't come out red on this in this software tool. But those dots are red when you do it in the browser. And the p-value a person can read says 0.50. So the p-value here is 0.05. So that's 5%. P-value of 0.05. Okay, and then the last one, 4.62, last one for this video. So here the hypothesis test is H naught is p equal 0.6 and HA p greater than 0.6. So I'm going to have to change that to 0.6. 0.6, good. And then I'm also going to have to edit the data. Editing the data is 52 out of 80. 52 out of 80. 52, 52 out of 80. 80, good. And of course they want me to generate, let's see here, it says, I'm just going to generate 1,000 samples and see what I get for 0.65. So 52 out of 80 is 0.65, so it says greater than, so I'm looking at a right tail, and I got to change this right here, got to change it to say 0.65 because that's the p-value I'm interested in. 0.65, okay, and it tells me that the dots 0.65 and above, and I don't know why they come out blue on this screen and red on the screen that I'm using here, but anyway, the point is that the p-value is about 21%. 0.209 is about 21%, and a person can tell just by looking at it that if you saw a sample like this in this context, if you were the null hypothesis people and you saw a sample like this, you'd say, well, that's a perfectly everyday sample. It's got a 21% chance of happening. You're going to have to do better than that to convince me that I'm wrong. Okay, all right, very good. I'm going to do the section 4.3 on a separate video, just trying to make things easier on the person who's downloading things. Okay, thanks. Bye-bye.